And me even longer. All right, well, wonderful. I would like to tell you about some of the work that we've been doing at the Scientific Computing and Imaging Institute, SCI, which we pronounce SCI, as in ski in Utah. So we're the SCI Institute. Before that, I always like to give a bit of a background of where we've come from at Utah and computer graphics at Utah, because I think most people don't really know this amazing history. So in the 1960s, we started a computer science program at the University of Utah, and the president hired David Evans away from Berkeley to come and be the first chair. And he told Dave, go out and get the very best people, even if you have to pay them 2 or 3 times their salaries, at which you never hear these days. But I think that was a great, great strategy. And the first person he hired was Ivan Sutherland, future Turing Award winner. So he did an excellent job in his first hire, hired Ivan, the father of computer graphics. His second hire was Tom Stockham, and also an amazing image analysis and signal processing person, National Academy. And those 3 set out a new department, and they focused on computer graphics and also a lot of other areas in hardware, et cetera, and trained these graduate students who really went on to change our world. So John Warnock was one of our PhDs who co-founded Adobe. Ed Catmull was one of our PhDs who co-founded Pixar and was the longtime president of Pixar. Just, I guess, 2 years ago, won the Turing Award. Jim Clark, who founded Silicon Graphics, and then left Silicon Graphics to co-found Netscape. The story there is that he invested, I think, $5 million into Netscape, and then within a couple of years, they sold it to AOL for more than $1 billion. And he continues to innovate. Healthion and WebMD are his as well, and many others. Alan Kay is one of our former graduates, another Turing Award winner. Nolan Bushnell is one of our graduates who invented Pong, the first video game, and started Atari. He sold Atari for a couple $100 million in the 1980s, and then he started Chuck E. Cheese Pizza Time Theater, which is still out there and very popular. And amazing computer graphics greats, Jim Kajia, Jim Blinn, Henry Garreau, et cetera. And I actually learned a tremendous amount from all of these people, and still stay in touch with most of them. Actually, just this past week, I've exchanged email with Ed Catmull and Jim Kajia and Jim Blinn. So it's an amazing legacy that we have here. And these are the smiling faces of the current Scientific Computing and Imaging Institute. And we're about 150 faculty, staff, and students, and represent the areas of scientific and information visualization, biological, medical, and geophysical image analysis, and scientific computing. And so everybody who's at the SCI Institute pretty much fits in one or often more of these different areas. And within the SCI Institute, we're a very interdisciplinary group. And so you'll see that our research centers, there are a number of research centers that the faculty lead. They're funded by the National Science Foundation, the National Institutes of Health, the Department of Energy, NASA, Department of Defense, and also we have a couple of centers that are funded by industry. And so this kind of just gives you a sense, from computational materials to integrative biomedical computing to extreme data management analysis and visualization, carbon capture simulation, how interdisciplinary we are and how it spreads over scientific computing and imaging and visualization. I like these images that Domo puts out every year about how much data is being created in 1 minute of the day. And on the right is the one from this past year, and on the left is the one from 5 years ago. And I think it's remarkable just to look at both the things that have the numbers that have increased. So if you look on the left at the Google numbers, it's like 2 million searches. And if you look on the right, it's 5.7 million searches per minute. Just the number of increases. The other thing that really strikes you is if you look on the right, you see several technologies that didn't exist 5 years ago. So Zoom and Slack and many others that are there. It's just it's incredible. So we have all this data, and every other day we are making as much data, more data now than from the beginning of humankind till the year about 2003. So it's enormous. And so how do we make use of this data? That's our grand challenge for now. And let's take a quick view of your brain and how it works. So here's a simplified view of the senses of our brains. And what strikes you immediately is how much of a visual creature humans are. So more than 50% of our brains are devoted to visual processing. And then we have touch and hearing, and taste is a very small one, but important. And the visual processing is also the fastest of our senses as well. And so if we can find ways to take all of that data and make abstractions and mappings to our visual processing sense in our brain, that's our best way to basically understand this data. And so that's what we're trying to do. I love this quote by Richard Feynman. So Richard Feynman, Nobel Prize winner in physics for his work in quantum electrodynamics. Richard was a very visual thinker, and he created what are now called Feynman diagrams. So those little squiggles you see on the stamp there on the right, and those are abstractions which basically were able to allow him to think about the complicated mathematics and interactions of the physics in order to reason about what was going on. And that's his van that he had painted with his Feynman diagrams that are there. And when James Leake wrote a biography and interviewed him many years ago, he asked Feynman how he thought. And he said, what I'm really trying to do is bring birth to clarity, which is really a half-assedly thought out pictorial semi-vision thing. I would see the jiggle, 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 the wiggle of the path. These are path integrals. Even now, when I talk about the influence functional, I see this coupling, I take that turn like it was a big bag of stuff and try to collect it in a way and to push it. It's all visual. It's hard to explain. And well, that's what we're doing. So we're trying to figure out how to make those successful abstractions in order to be able to better understand our data. Keep getting these requests for things, people showing up here. All right. Okay, so here are some examples of collaborations we've had with researchers throughout the world. In the center is a visualization of the largest simulation of a spiral galaxy forming by Elena Dongnia, who was then at Harvard and Smithsonian and currently at the University of Wisconsin. On the right middle is one of the largest combustion simulations in the world by Jacqueline Chen at Sandia National Laboratories. And in her simulations, she has one time step is about 4 terabytes, and then she has thousands of time steps, and so she's getting petabytes of data for a single run. We'll come back to that. And the left middle is some work by Mariah Meyer and biologists in looking at comparative genomics, and we'll talk about that more. But we have work here in fluid dynamics and in genetics and in cancer and many others. And so what I'd like to do is give you some examples of some case studies and stories that we have, and then talk a bit about some of the challenges that we're currently facing now, especially with larger high performance computing, and as we now move really truly to exascale. So let's start. All right, I'm going to start with the very small but large, and then go to the very large and large. So this is part of the Connectome project, which is an international research project by a number of neuroscientists around the world, and they're using electron microscopy in order to try to understand the connectivity within the brain. And you see that little red square there up in the upper left, that's the highest resolution of an electron microscope. So that's 4K by 4K. So that's your 4K TV that you're looking at night. They have this amazing system where they are able to cut the smallest piece of the brain possible, image it at the highest resolution of the electron microscope, dump out the data, and then repeat. So it's cut, it's image, it's dump, cut, image, dump, 24 hours a day, 7 days a week. And when it comes out like this, when you get all that data, it doesn't look like this because it needs to be registered. And so my colleague Tolga Tazizin, who specializes in image analysis, has tools to be able to put this all together. And then the real thing is to be able to go through the volume and be able to find the connections. So here we are going down in the depth, and we can't get the same resolution down in the depth as we can across the plane. So each one of these planes has a resolution of 150,000 by 150,000 pixels, and the resolution is 2 nanometers per pixel, 2 times 10 to the minus 9th meters per pixel. That's how high resolution is. That's how small this is, but you can see how much it changes as we go through the depth of this volume and how challenging it is to be able to follow those neurons from the first image you have all the way through that volume. And there are now actually international competitions on how to do this, and Tolga has actually led many of those with some of his machine learning algorithms to be able to do this automatically. So when we get done, we have 16.5 terabytes of data. And of course, what the neuroscientists want to do is be able to interactively visualize that. And so that's where we come in. And this is an example, a screenshot of that entire 16.5 terabytes of data on our Powerwall, which is 36 30-inch monitors put together to get 40 megapixels of resolution to be able to look at this. And I think of this as really like a new kind of microscope. When you think about all the new science that was developed when the first microscopes were being developed, because they could see things that no one else could see before. And that is what happened here, because we were able to interactively visualize the highest resolution data set that was ever created of the brain from electron microscopy. The neuroscientists would come and spend hours and look at this data, and they saw new structures. They saw new things that they'd never seen before, and they went and wrote Science and Nature and Cell and neuroscience papers on it. And then they started thinking about how to make this even higher resolution and to do simulations on this data. And so we're working with them now. The next version of this, which is coming very soon, will end up giving 100 terabyte data sets at even higher resolutions for us to work with. So the technology behind this is parallel ray tracing and rendering that we've created. So and I'll talk a little bit more about that later, to be able to do this in an interactive type of way, and also in some of the data streaming capabilities too, which I'll say more about. Here is a view of looking at those connections on just this one very, very small piece of the brain. And when I always think about how connected our brains are, and this is only one cell type, if you put all the cell types in there, there's just no space. And I guess gives you a really good idea of the complexity and the connectivity of the neural structures with our brains, and how complicated those neural structures are. When you think of parallelism in terms of the structures within our brains, it's amazing. All right, on to another project. This, I think, is my favorite current project we're working on. It's called Open Space. And we've all been to these great star shows at planetariums where we sit in the dark dome theater, and they fly us through the solar system and show us all kinds of really cool astronomical features. Of course, those are all production types of shows that take a long time and a lot of work to be put on. A few years ago now, NASA approached a group of visualization researchers and asked us, could you guys are you good enough now with your large scale visualization that you could do that kind of visualization on those domes with real data that we're collecting from our telescopes and from our simulations, and use this as scientific tools for investigation? And we said, yes, we think so. And so they gave us some money, some grant money, and which has just been renewed for another 5 years. And we've been creating Open Space, which is an open source project of visualization software that anybody can use for anything, but that is really focused on working in astronomy and astrophysics. And our colleagues are the American Museum of Natural History. That's where the Hayden Planetarium is in New York. In the middle is Anders Junnerman's group. He's the leader of the project at Norrköping University in Sweden, and he's the only visualization researcher I know who has his own planetarium. So that's pretty cool. We're in the upper right there in the University of Utah, and also Claudio Silva at NYU, one of our former faculty at SKI, and of course NASA. And this is just to give you a sense of the tool. So this is a multi-touch table, visualization table that we have, and this is Gene Payne, who's one of our software developers. He's just showing you how we can just easily move around the solar system. And the things to note, everything you see there is correct. All those stars are in the right positions. All those trajectories are in the right position. And we're going to grab data in real time from NASA image servers. So now we're going to zoom into the Earth here. And you'll see that as we get close enough, we're going to start pulling in image data from NASA. And there we are. We've got some image data. And he's going to locate, of course, Utah, and start zooming in, and we get a higher resolution as we go down. There's the Great Salt Lake, and we're going to move into the University of Utah and pop it up on our big display wall. And he's going to take his hands off of the controls now, and watch what happens when he does that. You'll see that once he takes his hands off, it moves. And the reason is that because the satellite moves across the Earth, and we're getting this data from that NASA server in real time, which I think is just, every time I see that, I think that's just really cool. So there's massive amounts of data that are coming through that, and the interactions with that. Now we're zooming out there. This is more recent, where we've taken the entire Sloan Digital Sky Survey, which was a 5-year mission through the Sloan Foundation, where they were mapping all of the galaxies throughout the universe. So each one of those dots is a galaxy, not a star, not a solar system. It's a galaxy. It just is amazing. We're going slow with this because it's easy to move those things too fast. But there are the galaxies within our universe. You'll notice there's a missing piece in that, and that's because of our own solar system, the Milky Way. We can't image through that, and so there's a piece there that's missing. But we're now working with the next Sloan Digital Sky Survey with Juna Kohlmeyer, who's the lead of that, and they'll have new sensors and new data that we'll be able to put into open space, so that astronomers and astrophysicists can be able to get that data and visualize and analyze that data throughout. And they can put it on a dome in a planetarium. They can put it on a power wall. They can put it on a desk. They can put it on their desktop, on anything. And we're now working on a virtual reality version of this, so that you can do this in VR. And I'm just thinking of when when we were kids and you like painted the stars and glow in the dark paint on your ceilings or something like this. Well, now kids will be able to put on their VR headset and look at the galaxies throughout the world. And that's kids of any age. So we think that's going to be really cool. All right. This one has a really great story to it about collaboration with scientists. And this is a system which is called Flow Render, and it's created by one of my colleagues, Chuck Hansen. And it's for looking at confocal microscopy in biology. It can work with any kind of imaging. But the story is that Chi-Ben Chen, one of the biologists at Utah who studies development, had helped create a transparent zebrafish so that they could watch the organs develop as the zebrafish grows. And so what they would do is they would have the zebrafish and a video camera on it 24 hours a day, and then videotape the growing organs in this video, or in this fish. And then the poor graduate student would have to spend months doing a tremendous amount of like hand segmentation of the organs using ImageJ and Photoshop and other things. And it was just taking enormous amounts of time just to do a single zebrafish. And so Chi-Ben Chen came up to Ski and said, I met with Chuck, so there's got to be a different way. And that started this long collaboration, which ended up with flow render, which is being used throughout the world for looking at confocal microscopy and many, many different applications, and continues to be research and development today. And I'll just play you a little video of one of our colleagues who's been using flow render.
Flow render is a tool that was developed for confocal microscopy data, and it's focused on giving biologists an easy to use method for doing visualization and analysis of 3D confocal microscopy data. So Gabrielle Cardin here at the University of Utah has found that flow render is a valuable tool for her research in the Cardin lab.
The Cardin lab works on congenital defects in muscle development, such as congenital diaphragmatic hernias. We're using it to image developing limbs and developing diaphragms, which are very complex three-dimensional structures. So I would say that we would be unable to do any of our work unless we had flow render.
That's the kind of thing we like to hear from our collaborators. They're just such beautiful images. And what's also cool is that the biological community has, they take a lot of images and make visualizations and photographs and things, and they have these international competitions, and people have used flow render and entered and won some of those competitions, which has been very cool. So this is Mariah Meyer, and this is a project which is in information visualization, so high dimensional visualization. And the thing about Mariah is that she works directly with the scientists. I think a lot of the visualization researchers out there, they kind of make these more general purpose tools, and they're just they're working much more on the algorithmic side, and it's like they just see data as data and how can they visualize it. Mariah actually embedded herself into the biological laboratories, read their papers, interviewed the researchers, looked at the tools they were using now, found out what worked, what didn't, and then started from scratch to design a visualization system that would work to solve that particular lab's scientific problem. And here are 4 of her biological applications, and they look different because they solve different biological problems. And one of my favorite examples of hers is called MISBE, and this is work with some researchers, geneticists at MIT and Harvard at the Broad Institute, and they're comparative genomicists, where they were trying to come up with models of linking chromosomes between humans and other mammalian species. And this is their first look at their model data in Mariah's tool. Well, those thick red bands and green bands you see are correct. Everything in that's else there, the orange and the brown and everything, is wrong. So immediately they looked at their model data and they knew that their model was wrong. And that's another great thing about visualization. It's very easy to know when you're wrong. So they went back to the drawing board and they worked on their model. After a couple of months, this was their best version, and they was still wrong. And so what they figured out was they had something fundamentally wrong with their model. And then they used Mariah's tool over multiple months in order to come up with what was then the experimentally verified correct model. And Mariah asked the head researcher, the PI of the lab, how long did he think it would have taken them to come up with this solution to their model without her visualization tool? And he said, quite frankly, I don't know if we ever would have gotten there. So I think it's just such a great example of how researchers in visualization and other collaborators can work together to solve problems that neither of them could have solved by themselves. One of the things to just say is that how interaction is so key to this process, where they're bringing in different data sets, they're doing statistical analysis and visual analysis. They have hypotheses, they're testing these hypotheses, and it's this iterative prototyping sort of work in order to advance their science. And I think it's a really great example. This is an older project, but I just really love it because the data is amazing. So this is the Michelangelo Project that Mark Lavoie did when he was on sabbatical one year from Stanford. Went over to Florence and was able to gain access from the Academia Museum of Michelangelo's David statue, and used a high resolution laser range finding scanner to scan the entire statue at sub-millimeter resolution. Here we're zooming in so you can see the eye, and we'll actually see individual triangles. There were so many of the triangles that he couldn't visualize the data sets. And this actually was our first, one of the first applications of our real-time ray tracer, where we can now do interactive lighting and shading and move around these enormous models. We had a video of this was in the Academia Museum for a while. Well, fast forward several years, and now there's a version that's much higher resolution. So this is now 2 gigapixels per frame, not megapixels like your camera, gigapixels per frame. It's almost 1 billion triangles. And we're going to zoom in at the same place in the eye. And at this resolution, you won't even be able to see a triangle. That's how high resolution is. You can see the little chip there. You can see the sculptor's marks, but you cannot see the individual triangles. And so this technology that's making this available is twofold. One is the parallel ray tracing that we've developed, and then also is the data streaming. So using Valerio Pascucci's system for data streaming, which is it's called PIDX, and it's a parallel system for being able to do streaming. I'll say a little bit more about that in an upcoming one. But it's the ability to stream these amazingly large, high-resolution data sets interactively that's been key for so many technologies and continues to be for high-performance computing applications as well as visualization applications. One of the cool things about this is that because this is so high resolution and we had complete access of it, we were able to see that somebody had carved the letters MN in his leg in the back, and that's still an historical mystery. Who carved MN when it was the statue used to be outside hundreds of years ago. And now, of course, you couldn't get close enough to it to do that, but probably some teenage kid. Anyway, it's pretty cool. All right, so this is another example of the streaming data sets, and this was work with NASA and also Lawrence Livermore National Laboratory. NASA has this really large-scale climate system, which is called the GEOS and Nature's Run, and they just keep it's this ensemble simulation for climate, and they just keep doing these simulations over and over again. It's currently about 3.5 petabytes of data. It is all open source, so you can download it anytime you want. So one of the issues is that because it's gotten so large that the visualization and you don't want to move that data, how are you going to be able to look at it? And so Valerio collaborated with researchers at Livermore and NASA, and using his VISA system, which is the parallel IDX data structure. What you're seeing on the bottom right is actually the interactive visualization of that stream data. And so what the PIDX is based upon is a type of compressed space filling curve data structure underneath the hood. And so there's a processing time that happens beforehand, but once it's in that format, then you're able to stream. And the big key here is that you're able to act on the streaming data with different operations. So you can do mathematical operations and filters as the data is streaming, and that's incredibly powerful. So you get both the streaming, but you also get the ability to act on and manipulate that data as it's streaming. And this now, there's actually, Valerio has a startup company based upon this, and there are just an enormous number of applications for this type of data streaming. And here are some of them. One on the top left is industrial agriculture, where you're flying drones in parallel over these enormous agricultural fields, and on the fly, being able to visualize and analyze that data, looking at places where there's not enough water, or there needs to be more fertilizer, et cetera. On the upper right is let's see, I didn't get that, is the 3D virtual reality of doing some 3D segmentation of those large neural structures. And we've shown that that is faster than the traditional way of doing things. There's some remote medicine on the bottom left, and the bottom right, left, I mean, and the bottom right, there's Valerio with one of the neuroscientists looking at that data on the large wall. And one of the high performance applications of this is another of my colleagues, Martin Berzins, who is doing some of the largest fluid dynamics simulations and combustion on these biggest DOE supercomputers. This is this clean coal fire boiler that's a large scale DOE process where they're funded project where they have 10 billion variables, and they need more. They need to scale up even more. One of the things that is key when Valerio and Chuck Hansen were doing the visualization for this was the need for the I/O. The scalability of the simulation was being held down by the inability of having fast enough I/O. And so that's where Valerio's PIDX for scalability came in. And Martin likes to show this slide of where they were getting these bottlenecks with traditional ways of doing the I/O of the data, and trying to do their visualizations, where threads and MPI were stalling out after so many thousands of cores. But with the data streaming architecture, they were continuing able to scale up all the way to 768,000 cores, and now more from this. But this really gets at one of the biggest challenges that we're seeing for high performance visualization right now, and especially as we transition into exascale levels, is that the processing of our data we can create way more data than we can move. And so the performances of I/O are just nowhere near what we need. And that's really started a whole new branch of visualization, which is called in-situ visualization. And so our ability to generate data is outstripped our ability to store and retrieve the data. Our traditional way of doing our simulation and visualization is you do the simulations, you write everything out to disk, and then you read it back in and you visualize it. So in this kind of post hoc visualization, and that just can't happen anymore, because at these levels of scales. And so what we need is a way to visualize the data as it's being simulated. And we're not storing the data. This drives the application people nuts, because they want all of their data. They want it there forever. They want to go back, and they want to be able to visualize, pieces of it, but it just is impractical. And so now we have a new paradigm for visualization, where we have to do this in sync with the processes that's going on. And there are a number of challenges. Just a couple of weeks ago in Hamburg, the supercomputing conference there was an entire workshop on in-situ visualization. I got to give the capstone talk in that, so it was really great. It's so new, and we're trying to figure this out. You'll see this paper that was published a couple of years ago, led by Hank Childs, and all of those people in that little box there are co-authors on that paper. So we got people who are the best people in the world who are doing high performance visualization together, and work together to try and come up with, what is in situ visualization, what are those challenges, and how are we going to be able to do this. So one of the ways that we're thinking about this is we can't deal with all the data. And so we need to come up with with more compact abstractions in order to be able to visualize what's there. So we can save some of the data, and what we do save, it better be important. And so one of the ways that one of the areas in which we're thinking about this is topological data analysis and visualization. So applying the mathematics of topology to data sets. And this has been shown to be very effective in scalar fields and vector fields. And now there's even work in some tensor fields of finding these abstractions that can summarize basically important features. So it's really feature detection and feature extraction. This is some work for projects by my colleague Bei Wang at the Ski Institute. So looking at flow field visualization in upper left, some astronomy work that I was involved with on the upper right. There's some climate data and weather data in the bottom right, and then even some brain network work that's been done with neuroscientists. And this is the project that I was working with astronomers and with Bei, and it was about these enormous, they call them data cubes from the microscope. So they're multiple petabytes of data, and they're both very large and they're very noisy. And we were able to use topological data analysis led by Paul Rosen and Bei Wang to come up with ways to reduce the noise and also find important features. And what you see in the top right and bottom right there is an example of how we were able to use this method called contour trees to find an important feature that was already known. So we could show that our method worked. And I don't know if you can see my mouse, but there's a little part there, this kind of a darkish orange on this, and that is a black hole. And we were able to find that black hole through these large data sets. So this is an ongoing project that we're continuing to work on with larger and larger data sets. A more recent project that was led by one of my former postdocs, Sudhanshu Sane, and is about how to find compact abstractions for very large exascale flow field types of data, and in cosmology, in fluid dynamics, and seismology. And he did this amazing work on doing Lagrangian analysis and finding these compact ways to represent interesting features within these flow fields. And in many of the standard flow fields are done with Eulerian types of ways, and by using these Lagrangian depictions was able to find a more compact representation to be able to do in situ visualization on these largest simulations. And here's some examples of looking at these Lagrangian representations of these flow maps. And the ones basically to look at, the one on the very left top is the ground truth. But the ones to be able to compare with are the two rightmost images, and one is an 8-fold reduction, and one is a 27-fold reduction. And if you look really closely at the 27-fold reduction, you can start seeing a little bit of difference. But with the 8-fold reduction, you really can't see any differences between that and the ground truth. And so we're getting order of magnitude types of reductions on this, and we're able to show in practice to be able to do this in situ while these large scale cosmology and seismology and other fluid dynamic simulations are running, to pull out this level of analysis and visualization for the researchers to look at. And it's such a compact representation that they can save some of these smaller representations, but not, of course, the entire simulation data that's there. One of the other huge challenges with these largest scale simulations is that you can't just use the usual standard uniform grids that we all know and love, and they have to use adaptive meshes. And so there's block structured adaptive meshes, and there's tree structured adaptive meshes, and lots of blends in between. And there's the AMREX is one example that many of these exascale projects are using in order to do the meshing structure for massively parallel simulations for adaptive meshes. the problem, the challenge for the visualization folks and the application folks is that pretty much all of the visualization software and algorithms are out there are based upon uniform grids. So ParaView and Visit, which are the two big DOE largest scale visualization systems that application researchers use, don't support adaptive meshes. They only support uniform meshes. And so if you have an adaptive mesh, you actually have to turn it into a uniform mesh in order to do isosurface extraction or vector field visualization or any or volume rendering. Well, that kind of defeats the purpose of your adaptive mesh. And so we have been working over the last couple of years to be able to create new visualization algorithms which can work directly on either block structured or tree-based adaptive meshes. And this is an example of work that we did on block structured adaptive meshes and looking at these really large scale colliding black holes that is from Stephen Hawking's group at Cambridge. And then also the landing gear for the NASA Exojet data set. We can do isosurface extraction, we can do volume rendering, and we have multi-transparency with that. Once this paper was published, we got lots of inquiries from the application folks out there saying, great, this is what I need. How does this work for tree-based adaptive meshing? And so that was our next research group, our next research project. And this was the subsequent paper that we were able to do. And this is a video showing the NASA Exojet where it's over 1 billion cells, and we're getting between 10 and 20 frames per second of being able to visualize this on this adaptive tree-based refinement scheme. And so this is not in situ, but we're now working on creating ways of being able to do this kind of visualization in situ for these exascale types of HPC projects. We're also working to be able to get this code into ParaView, for example, so that people can use this within ParaView directly, and with the Osprey renderer that's also in there now, the open source parallel ray tracing rendering that's supported by Intel. And you can see we can get pretty amazing detail on this in interactive rates on this highly adaptive mesh refined mesh. All right. We continue to try and figure out, different ways to visualize these extremely large data sets. This is one we have called Bricktree, which is a hierarchical data structure that we encode large volumes into these multi-level representations. And then we add detail as we move about and rotate into this. And so there's smart view dependent ways in which we're basically doing important space rendering on what you're looking at gets rendered fastest and then fills in while you're moving around and looking at the rest of the data. And I think this is the future of large scale visualization is going to be in situ, it's view dependent, it's multi-resolution hierarchical data structures, it's streaming the data as we're doing this to be able to visualize, and there are just enormous numbers of technical challenges that we have in the future to be able to get this to work. This is some more recent work on being able to take that really large scale data and visualize it at high resolution displays, because you have these high resolution displays where you have many data points per pixel on a standard monitor. Well, that's no good if you're going to do all that work to be able to simulate this highest resolution and then you can't see your resolution. Well, that kind of defeats the purpose. So, well, we need more pixels. And so we put together this low cost display wall with these Intel NUCs. And we wrote some software that's all open source so that you can build one yourself. If you've got 2 or 4 or 8 or however many displays, you can put them together and be able to create your own display wall and do this high resolution rendering. And so on your exascale high resolution simulation, you'll be able to see some of that detail that you need and zoom in over, in our case, 40 megapixels of resolution in order to see that kind of resolution. and some more progressive volume rendering. So this is, I'll skip that one. So here's another way of thinking about large scale complicated data is the local global question. So this is work with Hanwei Shen at Ohio State University and led by one of his graduate students and one of my postdocs. And it's an idea of, you've got these enormous complicated three-dimensional flow fields. Well, they just look like a pile of spaghetti that's been dumped on your screen. And so how can we find the trees within the forest? Well, this was the idea of this lens system where we deform the streamlines and go looking at those individual trees and making it so that it's sensitive enough that you can really do some exploratory analysis on this. And the thing about this is that because we're only operating on some local part of the data, this can be an enormous multi-petabyte data set, but we can get this kind of interactivity because we're only operating locally. And so this is another way of kind of getting over all of the data sets. We were working on this project, we realized, well, this is the same problem that neurosurgeons have when they're doing planning surgery for tumor resection. These are from diffusion tensor images of the brain looking at the white matter structures, and they want to avoid cutting through those white matter tracks. And so we were able, this is a prototype system, to be able to show them where those white matter tracks are and how they can go from outside of your head to your brain to be able to do that. And that's an ongoing project. We met with the neurosurgeons, and within 5 minutes, they had like 20 things that they wanted us to do and work with on that. So that's so stay tuned to see that one in the future. All right, let me end with one of my research projects, which is on uncertainty visualization. And I always ask people, when is the last time you've seen an error bar on an isosurface, including the ones that I've shown? And the answer is almost never. And so we have been working over the last several years with my students and postdocs and many other people in the community to come up with new abstractions and mappings of uncertainty that we can visualize for these complicated three-dimensional, often time-dependent visualizations and high-dimensional information visualizations. And it is incredibly challenging because the visualizations, the data sets are already very complicated to begin with, and you risk overloading the user's sensory inputs and their cognitive load if you start putting too much information in there. We found that right away when we started to add more uncertainty in there, that the application researchers were distracted by the uncertainty, and it was just too much for them to understand. And so we're continuing to try and figure out how to make this work. Well, some examples that have worked. This is work by my colleagues, Ross Whitaker and Mike Kirby, along with their student, Masha Merziger. And the idea was to extend traditional statistical methods for uncertainty to higher dimensions. And this is work that we also did with Mark Genton and Yin Sun at then Texas A&M. And Mark and Yin actually created something called this data depth functional box plot that they were able to extend Tukey's box plots to higher dimensions. And so what you see on the right is a traditional Tukey box plot. And then what you see there is in the middle is a flow past the cylinder. And if you understand the traditional box plot, you can now understand the higher dimensional version of that in a contour box plot. And then we created something called a surface box plot, which extends this even to 3 dimensions. And the folks at the National Center for Atmospheric Research saw this project and this visualization and wondered if they could use this and apply this to the challenging problem of hurricane prediction and the uncertainty involved. Anytime there's a hurricane, what we see is that they run 10 or so of these simulation models from around the world and trying to figure out where that hurricane is going to go. And you get these spaghetti lines that go all over the place, and they're very challenging and confusing to understand. Well, let's use a box plot, this ensemble, in this case, ensemble box plot. And again, if you understand the traditional Tukey box plot, you can much better understand, where the median is and the first standard deviation out and how that's going to work. And these are examples, snapshots that were done by NCAR from actual hurricanes Irma and Harvey that hit the United States, and we're able to visualize these. They haven't been used in the public yet, but they are being used behind the scenes for the researchers at NCAR. And some more recent work on this that we've done. This is with my former postdoc Tushar, who's now at Oak Ridge National Laboratory. And we started looking at none of the basic algorithms that we're using for visualization: isosurface extraction, volume rendering, vector field visualization. All of those algorithms are pretty much based upon linear interpolation, trilinear interpolation over structured grids. And they don't take into account error and uncertainty. And so our question was, well, when do these algorithms break down? At what level of uncertainty and error? And when they break down, can we create more robust algorithms that can then handle that added amounts of uncertainty and error and still get good answers? And this is some recent work on isosurface extraction, and this is the 2D contour plots. On the bottom left, you see some examples of the Kármán vortex street, and the one that's in the middle there, red is more error and blue is less, and the very bottom right is our implementation on this. So we were able to add a significant amount of error and uncertainty and still get good answers. And just this past year at the IEEE Visualization Conference, we extended this to the full 3D marching cubes case for isosurface extraction, and came up with these new ways of using entropy and probabilistic techniques in order to add uncertainty and still recover significant amounts of accuracy from these algorithms. And this is something I think we need to do with all of the visualization algorithms out there, is we need to be able to press them for how robust they are, for what levels of uncertainty and error, and then create new algorithms that are more robust. One of the real challenges for this, for exascale and high performance computing, is that these are almost all probabilistic algorithms, and they're using these huge Monte Carlo types of simulations. Well, that's not going to work so well if we are trying to do in situ visualization. So that's a whole new level of research. And there was a call just a couple of weeks ago from DOE on visualization, new research, and we're proposing new uncertainty visualization algorithms. And specifically, one piece is how are we going to be able to do these probabilistic algorithms in situ? We don't know, but we have some ideas. We need compact representations of probabilistic algorithms to be able to do quickly and interactively. So that's going to be interesting. All right, so let me end by saying, we work hard, and we have a lot of talented people, and so these are our productivity machines. We have 5 espresso machines in case 4 break down. So we have parallel espresso machines. It's very important. We also have ping pong table and a foosball table. We put this ping pong table, we got one on wheels, and that's our reception area. And we thought we'd just wheel it out every once in a while and then put it back in the closet, but it was so popular that we just left it out. And it turns out that ping pong seems to be the international sport of geeks. It's like everybody plays ping pong. So that's been fun. So thank you very much for allowing me to tell you a little bit about just a small number of projects that we have. You can head to the Ski Institute website, and we have all of our publications online. All of our software is open source. We're an open science, open data, open model, open software shop. And so, download some of our software, look at some of our papers, and if you have any questions, please let me know. Thanks very much.
Thank you, Chris. Thank you for an excellent talk. So I would just remind the audience to post questions. You can post questions on the chat, or you can indicate that you have a question and then unmute yourselves and ask the question. I already have several questions for you, Chris.
Okay.
I'll just have them on the chat. I'll just go over them one by one.
Okay.
Okay, so the first question coming from the audience is that the amount of data that is presented in the visualization, although good looking, is probably too much for humans to analyze. evaluate their models. Is there any ongoing research that looks for machine learning techniques to analyze the visualization itself?
Yes.
For example, look for anomalies in the visualization.
Yes, yes, yes. So as with pretty much every field, I think machine learning, you can't go to a conference anymore without the phrase machine learning in X or for Y or et cetera. And it's the same in visualization. So there are now entire workshops on machine learning for visualization and visualization for machine learning. It goes both ways. I gave a talk back in February on AI and visualization to kind of give an overview of what's been going on in the field. And there really are two prongs to it. And one is we're using visualization to try and better understand how machine learning algorithms work. So to unlock the black box of machine learning. And there have been a number of really interesting and useful tools that have been created, visuals tools to do that. And I'm happy to follow up with some of those. There's a lot of recent work in that. And then there's also machine learning for visualization. We just published a paper just a month ago on using machine learning for some flow field visualization. And it's basically using it to predict the path of vector field visualization. And so that we can do that more compactly. And we were able to get orders of magnitude speed up on some vector field visualization algorithms at very high accuracy. And so looking for features for speeding up calculations, for doing compact representations, and the kind of the modeling of these simulations. There's things going on in every way, shape, and form of both sides of ML for visualization and visualization for ML.
Thank you. My next question is, it's actually my question to you, right? So I think that the audience in this conference is very interested in how challenges in visualization affect our thinking about architecture and memory systems and networks and so on and so forth, right? So you mentioned I/O, you mentioned the I/O bottleneck, and I/O has been a very painful story in high performance computing. To this date, there is a huge problem with I/O, even in the very best machines that are out there. I was just browsing an SC paper from last year indicating that there's a 14 orders of magnitude difference in the I/O performance of the different jobs that run on super, which is so you can get anything from bytes per second to terabytes per second and anything in between. So I guess the question is, how can visualization workloads change our thinking or influence our thinking about how we do I/O and how we do networking and how we organize this machine? Because clearly the standard practices of doing I/O don't really work very well, right? Yeah. And there's no one size fits all kind of like approach here.
Yeah, that's right. And I don't have the answer, but I can say that one of the things that we're exploring, and in particular Valerio Pascucci is exploring, is trying to use data streaming as a faster mechanism in terms of getting the data from simulations and visualizations, and being able to operate on said data in visual ways. And I don't know of anyone who has used that yet for in situ visualization for these highest performance exascale computations, and I'm sure there are big challenges in being able to do that, but that's one thing that we're at least starting to think about. What are the right data structures and streaming architectures to be able to do that? The other thing that's from the other side of the picture is there's visualization tools that are being developed to better understand the architecture in I/O and the software stack. So Kate Isaacs is one such visualization, and it's like software visualization, information visualization, where they're looking at these enormous task graphs and the flow of the I/O and the data sets, and trying to use visualization to find ways to speed up everything from looking at an architectural point of view, but also the I/O and where are are there specific places in which, new algorithmic developments or software developments could be used? It's it's just such a problem. And I keep hoping that there's going to be, some new technology out there that's going to be the game changer, the disruptive technology that's going to come out, and all of a sudden IO is easy and fast, but it hasn't happened yet. And so we just keep struggling along, and it's pushing us in ways that no one ever thought. I mean, when I gave my capstone on in-situ visualization, I went back and tried to find out, where did that come up with in-situ visualization? And it really wasn't even a term until the 1990s, late 1990s. And then as the difference between the processing speeds and how much data we could produce and the slowness of IO throughout 2000s, like in 2010, there were hundreds of papers now on in-situ visualization, where there were 5 in 2000, and so it's pushing us in all kinds of different and new ways and new technologies. So it's challenging.
Yeah. The idea of using visualization to improve IO for visualization is intriguing. So Chen Ding has a question. Chen, you want to unmute?
Well, let me first say my appreciation of the visualization is always most fun because it's literally eye-opening. And thanks to the conference organizers for getting us the visually the best. To follow up what Dimitrios asked, I actually had similar question, is what's the implications for system builders like us? But then I want to move to another part, it's programming. Right? Visualization is building a tool for science, and programming systems is building a tools for writing in visualization tools. I'm curious, can you say a little bit how you build your visualization systems, programming languages, complexity of the size, complexity of the program, and also if I/O is the bottleneck, performance bottleneck, how important is program performance, parallelization, locality, for example?
Yeah, this is it's a really great question, and it's a really tough thing to do. And I'll say that, I'll say traditionally that what we were doing is, and it's still followed a lot, is we have to understand what the basic architectures are, and we have to write our visualization programs based upon what those architectures are, and as everything changes, as all of our visualization tools at the highest level have to change as well. So whenever NVIDIA puts out a new chip, or when Intel puts out a new chip, we have to basically rewrite and rethink about how the software and the algorithms are going to work. And so now there's more and more of these hybrid systems where things are, the architectures are all mixed, and there's just different amounts of GPUs and CPUs, and they have different bandwidths and different amounts of memory, and we have to be able to take advantage of all of those in order to get the scalability and parallelization of what we do. The locality and the parallelization are key. We're often writing stuff in C++ and C and then whatever languages in terms of CUDA or other, and they keep making more and more graphics languages, unfortunately, that complicates our life, to take advantage of getting the most performance out of whatever that hardware is there. And then, of course, the application scientists are also now using other systems. So Python has just kind of boomed in the last few years, where even high performance computing people are going to Python because it's so easy to use and so easy to prototype. Well, but Python scalability for visualization isn't there. So what are we going to do? So we actually did a project recently where we were trying to speed up volume rendering within Python. And there are some huge challenges from the Python programming language's point of view, that we could only get a certain level of performance because of restrictions within the language. And so there would need to be fundamental language changes within Python in order to get that scalability. And then the question is, well, do the Python people that kind of oversee Python, is that important enough that they would make those language changes in order to get the scalability for the visualization? So it's this back and forth all the time of pushing, on different architectures and languages. And then, we're trying to scrape out the most performance that we possibly can at every level, and it changes every day, and it will keep that way. But it's just such a moving target, and trying to, like the work that Kate Isaacs has been doing on some of the software visualization is also key and important to better understanding how the programming and interacts with the hardware and then the scalability that we can get in identifying these bottlenecks and, kind of zooming in and trying to fix those particular bottlenecks in performance and in IO, et cetera. So it's a really challenging, it will keep us busy forever, I think.
Thank you.
Chris, thank you. I have a couple more questions from the audience. The first is, could you talk a little bit about how any human-centered constraints influence the design of your tools?
Yeah.
And also considering the Feynman code that you had there, do you have any cases where you have to bridge what the users are asking for with what the users actually need? So
yeah, those are both really great questions. So human-computer interaction, HCI, is a huge field of endeavor, and it's so important in our design of how we create effective visualization abstractions and tools in the interaction. Every few years, graphics and visualization, they create these, like, what are the top 10 research questions in graphics or visualization? Ivan Sutherland did the first one back, I think, in the late 60s, early 70s, and there have been many of those. I wrote one in 2004 for visualization, and in all of those, HCI is on the list. That's one of the hardest nuts to crack, and the most important things to do. And of course, there's the Chi conference, and it's this huge, large, important conference on human-computer interaction. And so it is very, very important. And I think that's one of the things that's happened in the last, I'll say, at least few years, is the importance of design and taking into account our ways that we think and we understand, and our cognition process into the design process. And it's been really interesting, because the way it used to work is that there's a bunch of computer scientists who do visualization, and they just, create a window and start writing code and just kind of do what they usually do in the way of programming. Well, when you start actually incorporating people who do human-computer interaction and designers, it's entirely different. We get these designers and we start talking about what are the needs of the application and what it's supposed to do. And they immediately take out these sketch pads and they make 50 designs of different ways to look at the problem. And then they triage them and look at back and forth with the application people and the visualization researchers. And they start triaging until they get us, whittled down to a few designs. And then they start thinking about, actually making those into code and programming those. And then once we have those, we start doing user studies, which didn't used to happen. And we put those in the hands of the users, and we get feedback of which of our new prototype designs work better than others. And then we take those and we try to improve those. So there's this whole now, design life cycle based upon us and the human-computer interaction and user studies that didn't exist in that, 10, 15, 20 years ago. That's become much more prevalent in the field of visualization. And then what was the second part of the question? I've already forgotten.
There was a quote from Feynman, right?
Oh, yeah.
And, so are there circumstances where you have to
Yes.
understand exactly what the users are asking versus what users really need? And do you have to bridge a gap there, right? So that was
That's such a great question, because it happens all the time. I would say every time we talk with an application user, because they have their own view of the world and a limited set of tools. They don't know what the cutting edge is in visualization. We don't know what the cutting edge is in their particular research. And so it's often, we often have these researchers give talks to our visualization group. We have a visualization seminar every Wednesday at noon. And with the number of faculty we have and students, there's like 60 people that show up there, and we invite these people, the application people, to come in and tell us about their research, and then tell us what are the challenges, the roadblocks they're having in visualizing their data. And then we start talking, and often what it does is we say, well, this isn't exactly your problem, but it's kind of an analogous problem of work that we've done with someone else that could be of use. And we start kind of showing them, it's kind of the show and tell. They showed us of what they need and what they're doing, and then we start showing them, well, here's visualization tech A that you haven't seen before, and B that you haven't seen before, that might be useful. And then that often starts a collaboration where we can start with one of those pieces, but then create new algorithms and techniques that can help solve their particular application problem. So it's a great question, and it's also how we collaborate and how on a daily basis, and how important that collaboration is, that back and forth.
Okay, so very last question, Chris. So Chanding asks, how is scalability defined for visualization? And I would add to this question, are you aiming for just unbounded scaling, right? So you just keep growing the resolution forever, right? Or is there some limit that you want to hit there?
So I think that there's algorithmic scalability, which we're trying to push, reducing the complexity of algorithms and being able to get the much scalability as possible. But there's really a practical level of scalability that we're trying to achieve, and that's the one of interaction. And so we're really looking for how can we want that smooth interaction of, as the data sets get bigger and bigger and bigger, we still want to be able to interact with that data. And that's the challenge that we have. So we want, multiple frames per second. It's got to be a certain number of frames per second in order for us to be able to interact smoothly with that. And so that's where all of these issues about view dependence and hierarchical and multi-resolution data structures and streaming the data, et cetera, we're using those because we need interaction. If anybody's ever tried to visualize something where, you try to move your mouse and then, it just creeps, the image just kind of creeps along, and how frustrating that is. Like you have to go get a cup of coffee to get to your rotation or something. And that's just not practically viable. And so how do we do the data reduction? How do we do all these things? What are the techniques, the feature extractions, and where we can have 30 frames per second, and all of these become even more important and harder when we get to VR, because VR requirements are much higher to have that level of interaction, or people get sick. So you can't have your head move and then the image move, or you're not staying in your VR glasses for very long. And so that's an even more challenging in terms of scalability. We want higher resolution for our VR because we need it in order to have that VR experience and understand. But and we also need much higher interaction, but those are in direct conflict with each other. And so those are big open research problems that we're all trying to work on, is how do we keep that interaction as the data sets get larger and larger and higher resolution?
Okay, one very final question from John. So isn't visualization showing that scale and scalability of data management and control, which is the most vital problem in HPC, continue to go forward, can respond to mathematical and adaptive innovation? I don't know if you can read the question.
Yes, and that's absolutely the case. And we're always trying to, one of my early works with my students, Yarden Libnet and Hanwei Shen, was on isosurface extraction, where marching cubes was, the first isosurface extraction that Bill Lorenz and Harvey Klein did. The most cited paper in all of visualization and computer graphics. Like, it has more than 17,000 citations, but it had linear complexity in the search. And so as the data sets got bigger and bigger, it was untenable. And so one of my early papers was creating a new algorithm that they basically got a log X, type of scalability. And so we could get these orders of magnitude in terms of scalability. And then there was a progression of papers that continue to this day over the last 20 years, where there've been algorithmic and mathematical work on those scalabilities, where in oftentimes we're getting performance scalabilities because of the algorithmic developments, which are much better than what we would get scalability from the hardware developments. And so you want both, of course. You want the fastest hardware, but you want the best algorithms that go along with it. And I see those hand in hand. And so we absolutely are working to try and to create use mathematical and algorithmic innovation to be able to get that scalability.
Okay, we should all thank Chris in any way we have virtually. Chris, thank you very much.
All right, well, thank you. It's great to
great interaction. Kirk Cameron, our general chair, has an announcement for the audience before we break briefly until the next session. Kirk?
I can't share my screen yet. Maybe.
Chris, if you could stop sharing your screen. Yeah.
Thank you, Chris. And let me begin by just thanking everybody involved with the conference. Chris, fantastic talk. Very, some of the best talks to me make me ask the most questions in my mind. And man, every single challenge that you outlined this morning is a problem that the ICS community, I think, can really help with. So thank you again. I'm just going to quickly show a couple of slides, and then we're going to go to the next session. So I think you can see them now. I would also say that we have a great, this is the last day of ICS, probably the last time I'll talk to you all. And we've had a great conference so far, 3 fantastic keynote speakers, a lot of great papers, best paper awarded yesterday. And we still have a full day ahead, so of great papers, including some application papers, which was perfectly aligned with what Chris was talking about. So really quickly, ICS is going to be in Orlando in 2023. We had a steering committee meeting yesterday where this was decided. So I want to get you all excited for that. The FCRC, if you're not familiar with it, is a conference that happens every 4 years, and basically brings together this year in particular 12 conferences. Many of which I'm sure most of you have heard of and or published in. This is going to be a 7-day event. I can't change the fact that FCRC decided to host their conference in June in Florida, but I actually went to the University of Florida, so it's not too bad. Somebody said yesterday, at least it's not August. So hopefully we'll get some really good weather while we're there. It could be very beautiful, I think. And so it's going to be at the Marriott Resort there, just outside. In fact, again, I'm from Florida. It's like a mile from Disney World. So you'll see a lot of slides there regarding that. So there's all kinds of things to do, everything from Walt Disney World and the Universal Orlando parks and SeaWorld. So I think Disney has 4 parks. Things for you to do if you do bring your family along. But probably more importantly, there are all these conferences that are participating, conferences that many of us frequent, from the architecture and programming languages to algorithms, compilers, architecture. I think I said architecture already, energy, and of course supercomputing and high performance computing. So we're very pleased to be part of FCRC next year, and I hope that you'll join us. And with that, why don't we take a break here until 10:30? The next session will start. It's only about 5 or 6 minutes. And once again, thank you, Chris. We really appreciate you getting up this early. And it was a very exciting talk. Thank you.
My pleasure. Thank you.
So hello everybody. It's time to start a new session. Let's wait a couple of minutes. It was a short break, so we'll wait just a couple of minutes more. Meanwhile, Michael, you're the first speaker. Can you check whether you can share your screen?
Yeah, just a second. Do you see my screen?
Yes, yes.
All right, great.
Thanks.